Hi, I'm GOH ZEE XIN. I will do the demonstration for project 2. So in project 2, for the part 1, I need to use the tunnel SLD to design the schematic using the NAND configuration and with only 2 input NAND gate, and doing the timing simulation and then calculate the delay measurement and the power dissipation analysis. And for the part 2, I'm required to do the SDL using the tunnel edit and then simulate the layout by running the DRC LVS and extract the parasitic data. And then the parasitic data extractor will be used to run the post layout simulation and compare the result with the pre-layout design. So here I will first to open terminal, type with edit, and then here I will open my design. So this one is all of my design, and then I will show you my schematic design for the NAND gate. So this one is my design for the NAND gate. This one is the PMOS with 350 nanometer wide and 250 nanometer length. This one is also the PMOS. And then the bottom one is the NMOS with 350 nanometer wide and also 250 nanometer length. So this one is the design for the NAND gate. And this one is the input of A and B. And my output is Q. So this one is my output. So here I will click on cell, generate symbol, and then choose for this one. And the view I will need to type symbol, and then click on replace. So this one is my symbol generated. So here you can see input is A, and then the output is Q. So this one is my NAND gate simulated. And next I will use the symbol to do the simulation for NAND gate. So this one is my test bench for the NAND gate. And also need to note that this one is a 2 input NAND gate. So here I will use the pulse width to simulate it. So at here, we will set up first the simulation. Click on the simulation. So we'll click on the transient. And then aldo, print interval 200. Print start time is 0 nanosecond. Maximum time span is 1 nanosecond. And then for the general, I will insert the library file with the generic 250 model spice robot .library for different mode. And then I will run simulation. So this one is the simulation obtained. So we can see for the NAND gate 0, 1 is get 1, and then 1, 0 get 1, and 1, 1 getting 0. And for the 0, 0 we get 1. And so this one is the correct NAND gate simulation. And then next we will go to the LED to simulate for the layout of the NAND gate. And then I will go to the SDL to invoke the LED. So this one is my layout design for the NAND gate, and I will simulate the DRC. Since I already run previously for the DC run set, I'll click the DC run set and OK for the rules. And then run DRC. So since no result file means the DRC is completed and no error. Then we will run the LVS. So I'll choose the LVS run set previously. And then run LVS. This one I'm using schematic 1. Run LVS. So at here we can see the LVS report, and all the cell and the layout is the same, so the comparison result is correct. So this one is the report. And we can see also the LVS calibration report here. So before running PX, we will go to here to set up the variable. So the variable should be LVS path, and the value here is the default path. And then click OK. And then we will run the PX. So this one is my PX run set before. So I will click on it and run PX. This one is my output for the PX parasitic result. So no error found. And then next I will proceed to the Boolean design. So this one is my Boolean design, and we can see that I'm using 9 units of 2 input NAND gate. And this one is the G, and produce the G bar. And this one is the AB, and this one is the input CD. This one is the input E, and later I'll connect with the output of CD. And then for this one, and finally I will get the output of Y. So this one is my design for the Boolean expression. And then I will doing the same generate symbol, and then choose for symbol and click replace. So this one is the symbol generated from the Boolean. So this one is the A, B, C, D, E, F, G input, and the output is Y. So next I will doing the test bench for the timing simulation using the symbol. So this one is my test bench. So first I will do the simulation to verify my design is correct. So this one is the design where I'm using different period of time for A, B, C, D, E, F, G to get the output of Y and see whether the output is correct. So I will simulate. So this one is the output for my design, and it can be seen that all the design is correct. So this one is the output of my design, and it can be seen that the output is correct according to the design and the requirement. So for the different frequency, if I am using the design of F bar to get the output of 1, I will set all the remaining input A, B, C, D, E, and G to the 2.5 for the V1 and V2. So I can always get 1, and only F is doing the triggering for the period of time. And for different frequency, I'm using different period of time and the pulse width. So for example, at here, I'm doing period is equal to 6.67 nanosecond for the 150 megahertz and the pulse width 3.33 nanosecond. And if I'm using for 450 megahertz, then I will change my period of time to 2.22 nanosecond and the pulse width will be 1.11 nanosecond. And if I'm using the 1 gigahertz simulation, I will changing the period of time to 1 nanosecond and 0.5 nanosecond. So let's see the output. So this one will be my output. So we can see that only F is doing the triggering and contribute to the output of Y, and the remaining is equal to 2.5 and constant value to avoid the interruption. So we can see when F bar, then we can get Y equal to 1. And from here, we can calculate the delay for the difference of input. So here we can set the cursor here at 1.25 and also set the cursor at the output for 1.25 to get the difference, and the difference is our TPLH or TPHL. So next I will do for the layout of the Boolean. So I will open the schematic and click on the SDL. So at here we can see that this one is the first NAND gate design. So the first NAND gate I will connect to G, and the second NAND gate is connected to A and B, and the third NAND gate is connected to C and D. And then for the output, connected to the remaining gate, just same as the Boolean design inside the schematic. So from this one, I will do the simulation for the DRC. And then using the run set that I already set. And then run the DRC. So from here, no result found, we can say that there is no error for the design. And then next, I will go to simulate for the LES. And then using the run set before. And then run LES. So this one is the comparison result and the report for my Boolean design. The comparison is same, so it's correct. And we can view the LES report here. So it's correct for the overall comparison between the layout and the source. And then next, we'll do the simulation for PX. So also same, click on the PX. And then also the same, click on the PX run set. Okay. Run PX. So this one is the PX report we get, and no error is shown. So means it is successfully generated. So next we are going to do the simulation for the new calibrate view. So I'll click on the test bench 1. And at here we'll import the calibrate view, and here calibrate, and then make sure here is we import the Boolean 1, and then import the calibrate view and import the schematic. And then we click import and get the design. Before doing this, I will simulate once again for the schematic design and save the WAV file. So for here, I will save it and save in this one, and then my library, and then this one, and then save. So next, I will do the simulation for the calibrate view. So again, click the simulation. So this one is the simulation design for the calibrate view. So here we can see, and then we have opened the previous design for better comparison. So here we will move the Y. So it can be seen that actually all the design for pre-layout and the post-layout is the same. But from here we can see that actually there is some difference in terms of timing between the pre-layout for output and the post-layout for output. So next we will move to the simulation for the timing according to the frequency, just like just now. So here I will also simulate again for the schematic design, just like inside the test bench 1. So same at here we will save inside my folder, and then choose the TB2 and save it. So for better comparison, at here I'm doing only for F bar to get the obvious difference between the pre-layout and the post-layout timing. And then at here I will also doing the calibrate view. So this one is my output for the calibrate view. So here I'm also simulate for FOD, and then I'll open for the schematic design, and so I'll open the pre-layout design. So here we can see there's a bit different. So I'll zoom. So here you can see the difference between the timing, and then I will measure the TPHL and TPLH for the post layout design, and then compare with the pre-layout design. So this one is the TPHL for the post layout design, which is more different with the pre-layout design. And I will also apply the same method to the TPLH and also for the different frequency. So all the objective is achieved. So that's all for my demonstration video, and thank you.